Hello everyone, I am Avijit Roy and welcome to our presentation. Today I am going to present a decentralized reinforcement learning system for patrol routing. So let's begin. The urgency of first response in emergency situations is a critically important aspect of public services. Emergency response services are tasked with responding as quickly to the emergencies as possible, given the existing resources. But the existing resources are limited, so emergency response services has to use the resources intelligently. The problem of optimizing first responder resources are most commonly studied in the context of police patrolling. Large-scale field studies attest to a substantial deterrence effect from policing patrol officials prominently in the known hotspot positions. The time a patrol vehicle takes to reach the crime spot after getting a call is known as response time. We want the response time to be minimum. One easy solution to this is to allocate a large number of vehicles, but this is practically not possible after some time because the number of vehicles has to be limited after some time. So we need to optimize the available resources. In the case of UP 112 that we are studying in this work, the police department has around 700 patrol vehicles for a population of 220 million people. So, with this resource constraint, it becomes even more important to place the vehicle intelligently. Police department daily receives around 50,000 calls, among which around 5,000 requires emergency response. The average response time in urban and rural areas are 15 and 20 minutes respectively, and each vehicle travels around 70 kilometers per day. So, our aim here is to reduce the response time using the available resources and also to reduce the operational cost by reducing the average distance traveled by each car per day. Previous research tackling similar problems uses graph partitioning and network flow optimization. Here, the maximum coverage patrol routing problem is modeled as a minimum cost network flow problem. Another approach is to tackle the problem as two-player zero-sum game. Here, attacker tries to destroy one of the multiple targets and the defender tries to capture the attacker before attacker reaches its target. These approaches tries to maximize the time spent in the crime hotspot areas, but completely ignores the patrolling of non-hotspot areas. Also, they don't consider a real-life constant, that is fuel price. In our approach, we take care of both of these problems. Reinforcement learning based solutions that were proposed earlier were centralized and overly complex. Also, they lack real-life data. We test our system using real-life data. Our system is decentralized and highly scalable. Also, it is easy to test and interpret the results of our system. We design our rewards keeping in mind three factors. First, the agent needs to be close to the crime location. Second, agents need to keep distance among themselves to maximize area coverage. And third, any movement is costly. So, we design three types of rewards: instant reward, proximity reward, and step penalty. Agents get instant reward when they reaches a crime zone within some constant amount of time after the crime occurs. The earlier the agent reaches the spot, the higher the rewards. So, in simple words, the instant reward diminishes with time. To promote distance among agents, we use proximity reward. The higher the distance, the larger the reward. And also, to restrict movement, we use step penalty. Under the hood, we divide the entire area covered by the emergency services into district-wise zones, approximately identified by rectangular based boxes. We then divide it into m cross n grid. We do not consider any pathing constant in the current version of the algorithm. We generate the routes on a daily basis and it contains location of each vehicle in 24 points in time, resembling the 24 hours of the day. At every step, each vehicle receives position of other vehicle and location of crime to calculate the reward obtained. This is a screenshot from the application that we have built. It contains 10 vehicles and the colors in the background shows the crime density. The red shows that it is a high crime prone zone and the blue shows that it is completely low crime prone zone. And where there is no color, it shows that we don't have any data from that location. In this slide, we show some basic validations that we have done. The first picture on the left shows that with the increasing number of iterations, the reward accumulated increases. It resembles that our entire system learns. With the number of iterations, it is able to meet the target that we have given it and it is able to capture more reward. If we see the picture on the right side, it shows that with the increasing number of agents, the reward accumulated increases and at last it plateaus. It also resembles that the more number of agents we use, the reward will be higher, which is obvious, and along with that it also shows that we achieve optimal behavior of the entire system well before using a large number of agents. So our system works in that aspect as well. Here we show some interesting results that we have observed. If we see the image on the left side, we measure response time to calls with respect to the number of agents in the system. We use distance of the nearest agent when a call occurs as a proxy for the response time. We observe from the figure that response time drastically decreases initially, then the rate of decrease reduces slowly and the curve flattens and looks reasonably exponential. These results clearly indicate the possibility of optimizing the number of actively patrolling agents without compromising very much on the response time. Thus, these results support the basic premise of our system that we can cut down on miles driven without affecting the response time very much. Now, if we see the image on the right side, we measure response time with respect to the distance traversed by all the agents for different values of step penalty. We observe from the figure that when there is no step penalty, the agents tend to move more and it decreases with increasing step penalty. By adding step penalty, we can see that the fleet as a whole travels less. More importantly, a more static fleet actually sees lower response time on average. We choose a small area within the district and ran 3 experiments with high, middle and low fuel consumption imperatives for a single vehicle by controlling the step penalty and show the resultant routes. We visualize our observations in this figure. The key point to note is that as fuel consumption becomes increasingly more prioritized, the patrolling routes reduces its length, covering lesser area and prioritizing the more likely locations of call organization. We asked 12 people to score patrolling routes drawn by human and the system out of 100. If we see the results, we can see that human performed better, but the system also is very near to the human performance. We are collaborating with Kanpur Police to test our system in real life. And after we test our system, we can tell if there is any improvement using our system. This is a first path attempt to solve a real life problem, and we hope that we can improve it further in the future works. Thank you. Thank you all.